right, so we're going to consider four thermodynamic processes today. The first being called an isothermal process. Let's see what Theo the thermometer has to tell us here. When we look at the word isothermal, iso means same, therm means temperature. So as you might imagine, an isothermal process is one that takes place at a constant temperature. In other words, the temperature does not change. Now, the system we're going to consider in this process and in all four processes we look at today is that of an ideal gas. Okay, and we're going to confine our ideal gas inside of a cylinder with a piston at one end to be able to trap the gas. Now, to ensure that this process takes place at a constant temperature, we put our system, okay, our gas and our cylinder and piston in contact with a heat reservoir, which remember is an object that is considered so massive, so large, that any amount of heat that gets transferred to or from it will not change the temperature significantly. So in that sense, we can consider the process to be taking place at a constant temperature. Now, when we look at what this process means on a PV diagram, remember that's a diagram of the pressure of the gas as a function of volume. We start by taking a look at the ideal gas law. The ideal gas law is alive and well here for an ideal gas. And when we look at PV equals nRT, remember the right-hand side of that equation, the number of moles is constant because we're looking at a trapped amount of gas. The ideal gas constant, by definition, is a constant. And in this case, the temperature is constant. That's what we mean by isothermal. So the entire right-hand side of that equation is a constant. In other words, the pressure of the gas times the volume of the gas is a constant. When we graph that relationship, PV equals constant, the graph turns out to be a hyperbola. This is really one branch of the hyperbola here. And because this is a graph of an isothermal process, we give it a name. We call that an isotherm. So we're now in a position to apply the first law of thermodynamics to this special case of an isothermal process for an ideal gas. Now, remember the first law of thermodynamics is really nothing more than a statement of the law of conservation of energy applied to a thermodynamic process. It tells us the interplay between the internal energy of our system, in this case an ideal gas, the amount of heat added to the system, and the work, the net work, which is either done on our system or by the system. So it turns out that for an ideal gas, there's a very simple relationship between the internal energy of the gas and the temperature of the gas. Okay, this expression 3/2 nRT, we will derive in our next unit on kinetic molecular theory, but for now you're going to have to sort of take on faith. This is how you calculate the internal energy of an ideal gas. Now you can see that what we're really interested in is changes in internal energy rather than the absolute internal energy itself. And you can see here that the change in the internal energy of an ideal gas is related to the change in temperature of the gas, which you can easily see is 0. Okay, by definition, an isothermal process is one that takes place at a constant temperature. In other words, the temperature does not change, which means delta T is 0. And we can then conclude that the change in the internal energy must be 0. When it comes to work, we have this general expression on how to evaluate the work done on our system. And since we're talking about an ideal gas here, okay, we can solve the ideal gas law for pressure and substitute it into our work expression here, in for P. And we notice here that once again, okay, this expression nRT, okay, number of moles times ideal gas constant times thermodynamic temperature, is a constant for the isothermal process, which means it can be taken out of the integral sign. so that when we actually evaluate the integral and the limits of integration as a gas goes from its initial volume to its final volume, okay, we end up with this expression here, that the work done on the gas is equal to minus nRT natural log of V final over V initial. All right, I want to point out here that when we look at this expression for work, the work done on the gas, let's look at it. If the gas undergoes an expansion, so the final volume is greater than the initial volume, then the natural log term is positive and our expression for work is negative, which means that a negative amount of work being done on the gas is synonymous with a positive amount of work being done by the gas on the environment. So in this case, we get useful work out of our gas, okay, as that gas expands doing work on the environment. So in this sense, you can sort of think of it like the piston maybe in the internal combustion engine of your car, that as the gas expands, although we can't really consider that process isothermal, but we can say that as the gas expands, okay, you get work being done by the system, useful work out of the system. So, and I should say likewise, if we're talking about an isothermal compression so that the final volume is less than the initial volume, you see that the natural log term is negative, which makes our work expression positive. In other words, we get positive work being done on the system. Okay, work from an external agent must be done on the system, okay, to force the piston, okay, to reduce the volume of the gas. So when we apply this to the first law here, okay, incorporating these expressions here, we see that the change in the internal energy is 0, okay, and we incorporate our expression for work. We see here that the heat that is added to the system is related to the work that is, okay, being done on the system here. So if we want to get positive work being done by the system on the environment, okay, we must add heat. That's what happens in the expansion. If we look at an isothermal compression, okay, we must remove heat from our system so that it maintains a constant pressure as the gas is compressed. All right, so let's now apply what we learned about isothermal processes for an ideal gas. Let's apply this in an example. Here we're told that a scuba diver swims at a depth of 25 meters where the pressure is 3.5 atmosphere and the water temperature 300 Kelvin. Okay, the air she exhales forms bubbles 8 millimeters in radius. How much work is done by each bubble as it expands upon rising to the surface? So we always start by defining our system, and our thermodynamic system in this problem is that of a bubble, which we will consider to be an ideal gas. So let's see here, we've got a bubble. Notice what happens to this bubble as it rises to the surface. Okay, as the pressure decreases on it, the bubble expands. We're asked to find how much work is done by each bubble on the environment as it expands. So let's take what we have said here, starting with the fact that if we assume the bubbles remain at a constant temperature of the water, okay, then we can consider the process to be isothermal, assuming there's not a big temperature change between the bubble going from 25 meters down up to the surface. If we're asked to calculate the work, we can use the result we derive that the work done on the gas is minus nRT natural log of V final over V initial for an isothermal process. Of course, the work being done by the gas, which is what we're asked to find in the problem, will simply be the opposite of that. But in looking at that expression, you see that we need to know really three things: the initial volume of the bubble, the final volume of the bubble, and this expression nRT. So the initial volume of the bubble, well, that's easy. We can determine that from the dimensions that are given, considering each bubble to be a sphere. okay, of radius r. So that initial volume is simply 4/3 pi r cubed. Okay, so that's done. The final volume of the bubble, well, we can find that by actually applying the ideal gas law. Okay, remember that we're given information about the initial pressure of the bubble at 25 meters down must be 3.5 atmospheres, whereas we will assume that when the bubble reaches a surface, okay, the pressure there is simply atmospheric pressure, which we'll assume to be 1 atmosphere. The ideal gas law suggests that for a constant temperature, okay, this relationship P pressure times volume is a constant. That, you may recall, is simply Boyle's law. So we have a relationship here that the initial pressure times the initial volume of the bubble must be equal to its final pressure times final volume. Plugging in the information we have about initial and final pressures, you can see then that we have this volume relationship, that the final volume of the bubble must be 3.5 times the initial volume. Okay, so now that we know the initial volume, we now know the final volume related to the initial volume. We just need to know this a value for nRT, but don't forget about the ideal gas law. Even though we're not told n directly in the problem, so we don't know the number of moles to be able to figure this out directly, we do know that nRT is equivalent to the pressure times the volume, which we do know. So plugging this in, we find that the work done by the bubble on the environment is equal to the opposite of negative nRT, natural log of V final over V initial. Okay, so here the work done by the bubble, okay, should be positive as the bubble and gas inside of it expand. And at this point here, it's simply a matter of plugging in our numbers here. Okay, the initial pressure, 3.5 atmospheres, we'll convert that to SI units. So we use the conversion factor. There's 1.01 times 10 to the 5th pascals in an atmosphere, an SI unit. Okay, and the initial volume, 4/3 pi times the radius cubed. Don't forget to convert that radius to meters. Okay, times the natural log of, okay, the ratio of final volume to initial volume, which is really nothing more than the natural log of 3.5. Okay, we do the number crunching, and it turns out that the work done by the bubble on the environment has a value of 0.95 joules. All right, so the second of these 4 thermodynamic processes we're going to consider today is what we call an adiabatic process. And by definition, an adiabatic process is one where no heat is allowed to flow into or out of our system. In other words, the net heat transfer to or from our system is always 0. So when we're describing our system, as in the case of the isothermal process, we're going to consider an ideal gas which is confined to a cylinder with a piston, okay, and that gas will be allowed to expand or contract. That piston is free to move. Now, how do we ensure the process is adiabatic? In other words, that no heat flows into or out of our system? Well, one possibility is that the process takes place so quickly, okay, that heat has not had time to flow. Okay, heat transfer by thermal conduction takes time. So in the event we consider that the motion of the piston to be very quick, okay, we can consider the process, we can approximate the process as adiabatic. The second possibility, we can allow a process to occur slowly so long as our system is well insulated. It's thermally insulated, so no heat is allowed to enter or leave it. So that's what I'm trying to show you in the diagram here. What does the adiabatic process look like on a PV diagram? Well, to start out, we're going to look again at the isothermal process and start there as a basis for comparison. Remember, the isothermal process for an ideal gas, our graph, our isotherm, was nothing more than a graph of the relation, the pressure of the gas times its volume was a constant, since the temperature was constant. And we saw that this was simply a hyperbola. This came from the ideal gas law. Now, there's also a gas law that applies to an adiabatic process. It's what we call the adiabatic gas law. We will derive it in a future lecture, but for now you're going to have to take it on faith. What's important to see about this, however, is that we have a similar relationship, that the pressure times the volume of a gas, you see there that constant, the volume is raised to this constant gamma, and gamma turns out to be nothing more than this ratio of the molar heat capacity at constant pressure compared to that at constant volume. And we'll talk about that later. What's important to know now is that this ratio of Cp over Cv is a number greater than 1. So in other words, the constant gamma is a number greater than 1. Okay, usually somewhere around 1.4. So that when we actually look at the graph of pressure times volume raised to a power that is slightly greater than 1, we see that our graph, okay, what we call an adiabat, is going to be steeper than the isotherm, okay, because that constant gamma is greater than 1. Alright, so let's now turn our attention to the first law of thermodynamics and see how the first law applies to an adiabatic process. So as you recall, for an ideal gas, the internal energy has this direct relationship with temperature, and the change in the internal energy of an ideal gas is equal to 3/2 the number of moles times this universal gas constant times the change in temperature. Now, what's important to remember is that for an adiabatic process, the net heat that is transferred to or from our system is 0. So that when we now apply the first law of thermodynamics, we see that the work that is done on our gas is equal to 3/2 nR times the change in temperature. So what this tells us is that if we look at the ideal gas that is confined to a cylinder with a piston on it, as work is done on the gas in compressing it, that is in exerting a force on the piston to compress the gas, work is being done on the system. That tells us then that the temperature of our system, the temperature of the gas, is going to increase. Now, conversely, if we let the gas expand and do work on the environment, as that piston is moving outwards, we would see that work is being done by the gas on the environment, or a negative amount of work is being done on the gas, in which case the temperature of the gas will decrease. That is, the temperature will drop. So let's take a look at a few examples here. And the first example we consider is not one of an ideal gas, but is an adiabatic process nonetheless. And this is something you can do at home. I would suggest taking a rubber band, making sure it's clean here, because you're going to want to touch it to your lips. And if you hold the rubber band loosely in your hand and you feel that its temperature with your lips. The lips are a very good temperature sensor because the skin there is thin and you have a lot of blood flow close to the surface. You can nicely gauge the temperature of that rubber band. Then what I would ask you to do is to do work on that rubber band and stretching it several times. Okay, that is, stretch it, relax it, and quickly touch it to your lips. We can consider the process here adiabatic because we're doing this very quickly. And what you should notice is that it should feel warmer when you place it in contact with your lips. Now, when we think about this, the sudden stretching of the rubber band, we're doing positive work in the stretching process. And according to the first law, the work that we're doing on the system should cause an increase in internal energy of the system. In other words, that increase in internal energy is recognized by the increasing temperature that you observe. Now, in this next example of an adiabatic process, we will consider the case of an ideal gas, and a rather important case at that. We will look at uh, the gas, okay, that is the fuel-air mixture inside one of the cylinders of an internal combustion engine. And in this problem, we're told that this gasoline engine, we're going to consider 0.25 moles of gas expanding rapidly and adiabatically against the piston. So inside of the internal combustion engine, we have both compressions and expansions. In this case, we're going to look at an expansion. And we can consider the process to be adiabatic because it occurs so quickly. So heat has not had much time yet to flow by thermal conduction. We're told that in the process the temperature drops from 1150 Kelvin to 400 Kelvin. How much work does the gas do in this process? And once again, we're considering the gas to be ideal. Well, instead of calculating the work directly, okay, we can use the first law since we don't know the value of gamma in this problem. It's not told us. So let's use the first law of thermodynamics, what we derive for the adiabatic process, where the work done on our system, the work done on our gas is exactly equal to the change in the internal energy of our gas. And since that change in the internal energy of a gas for an ideal gas is simply 3/2 nR times the change in temperature, that information we do have. So here, plugging in our numbers here, we see that we plug in the 0.25 moles for N. Make sure to use the universal gas constant in its SI unit system. And we include our initial and final temperatures here. And we find out that minus 2300 joules of work is done on our gas. Or conversely, we can say the work done by the gas is simply the opposite of this, which is 2300 joules. So as that gas expands against the piston, okay, we end up getting work done by the gas, or 2300 joules of useful work being done on the environment. All right, so in this last example of an adiabatic process, we'll take a look at a rather interesting and important adiabatic process. This is what we call the adiabatic cooling that we see when a gas gets compressed to the point where it becomes liquefied. Now, we can consider this process to be adiabatic because it occurs quickly. And although we can't consider the gas to be an ideal gas since it is becoming a liquid in this process, we can apply the first law of thermodynamics, which suggests that the work that is being done on the gas and compressing it and turning it into a liquid is equal to the change in the internal energy of the system here. So as I said before, we can't consider the gas to be ideal, but work is done on the gas causing this change of state as that gas is forced into the liquid state. Now, if we look at the diagram above here, okay, as work is being done on the gas by the compressor motor here and compressing it, what we see is that that gas is being forced into the liquid state here, okay, and as those gas particles are moved closer together, as the spacing is removed between the particles and as they become a liquid, we see that the change of state brings about a release of that heat of vaporization. Okay, so as the gas particles become a liquid, energy is being released in the form of the heat of vaporization. So that causes the gas particles to actually lose potential energy, but that energy has to go somewhere. Where does it go? It goes into the environment and it heats up the environment, causing an increase in temperature. This is what happens in the condenser coils of this unit. Okay, and as you well know, for example, if you look at the condenser coils in the back of a refrigerator, we see that they heat up and that energy gets released into the environment. Okay, very often you notice that warm air coming out of the back of your refrigerator. Now, what happens next over here on the right-hand side of the diagram, we see here that expansion valve is released, and as that expansion valve is opened, that liquefied gas under pressure rapidly expands. Okay, and in that rapid expansion, it is absorbing energy from inside of your refrigerator to once again enter the gaseous state, right? To once again regain that heat of vaporization to turn the liquid once again into a gas. Okay, and as that happens in these evaporation coils here, that energy has to come from somewhere. That heat of vaporization is coming from inside of the refrigerator, okay, causing a drop in temperature there, okay, as those gas particles gain energy in going from the liquid to the gaseous state. This is what causes the cooling inside of the refrigerator. All right, so this third type of thermodynamic process we look at is what we call an isobaric process. And to gain a little insight about its meaning, let's defer to our favorite test tube here, Timmy the test tube, and see what he has to say. He says, well, isos we know means same, bar means pressure, so as you might expect, an isobaric process is a process that takes place at constant pressure. So the system we'll take a look at is one we're quite familiar with now. That is an ideal gas that is confined to a cylinder with a piston on it. But here the piston is going to be allowed to move freely up and down in order to maintain a constant pressure. So as the gas either absorbs or transfers heat to the environment, okay, that piston is allowed to move freely up and down, okay, to maintain a constant pressure. So in this case, if the piston is exposed to the atmosphere, okay, then we can assume that the pressure of the gas will be maintained at atmospheric pressure. What does this process look like on a PV diagram? Well, it's actually quite simple. Since the pressure is constant, we expect it to be a horizontal line. Now, we call the graph of an isobaric process, we call that an isobar. And as you might expect, we can look at either an expansion or compression of the gas, either an isobaric expansion or compression. In the case of an expansion, our system will start out at some initial volume and end up at some final volume, okay, in which case the work done on our gas is simply, okay, the area under the graph, which in this case will be the area of a rectangle, okay, which is quite easy to find. All right, so let's see how the first law of thermodynamics applies to the special case of the isobaric process. And once again here we see that the change in the internal energy, okay, for an ideal gas is given by this simple expression here, so don't forget about this when it comes to problem solving. But let's turn our attention to the work done on the system in an isobaric process, and we see here our generalized expression for work. Because that pressure is constant, it can be taken outside of the integral sign, in which case the work done on our gas is simply the opposite of the pressure times the change in volume of the gas. Now notice here that in the case of an isobaric expansion, okay, where our gas is allowed to expand, okay, the work done on the gas is negative. In other words, the work done by the gas is positive as that gas expands, doing useful work on the environment. Conversely, if we look at the isobaric compression, okay, where our final volume is less than our initial volume, we see that the work done on the system is positive, okay, which only makes sense because it takes work done by an external force, okay, to be able to compress that gas, okay, at a constant pressure. When it comes to applying the first law of thermodynamics here, we see, okay, that we can substitute our expression for work here, okay, the simple expression of, okay, the pressure times the change in volume. And then, of course, if you're talking about the special case of an ideal gas, okay, know that you can substitute the change in internal energy expression in there. So we see here that in the case of an isobaric expansion, okay, where P delta V is positive, we see that the negative sign indicates that our system is going to lose internal energy, okay, as that gas expands, doing useful work on the environment. All right, so let's take a look at a few examples of isobaric processes. The first example is very straightforward and very important. If you think about it, pretty much all chemical and biological processes taking place on the Earth's surface are taking place at a constant atmospheric pressure. So these processes are, for the most part, isobaric. A more quantitative example here, if we look at a gas that is enclosed in a cylinder fitted with a light frictionless piston and maintained at atmospheric pressure, once again that piston simply being free to move up or down, what happens when we add 1400 kilocalories of heat to the gas? Okay, well, as you would expect, the volume is going to increase. Okay, that piston is going to move outwards, and we're told here the volume changes from 12 cubic meters to 18.2 cubic meters. We're asked to calculate two things. First of all, the work done by the gas, and second of all, the change in the internal energy of the gas. So we note here the process is isobaric. So the work that is done on the gas is obtained from the simple expression minus pressure times the change in volume. Okay, we plug in atmospheric pressure for the pressure, and the volume changes. That is the final volume of 18.2 minus the initial volume of 12. We get a negative value for the work done on the gas, which, said another way, saying the work done by the gas is the opposite of that, which is positive, or a positive 6.3 times 10 to the 5th joules. So as that gas expands, the piston ends up doing work on the environment in the amount of 6.3 times 10 to the 5th joules. To calculate the change in internal energy of the gas, we use the first law. Okay, so we must add the heat added to the gas. So we'll convert the 1.4 times 10 to the 6 calories into joules, okay, using the mechanical equivalent of heat here. Okay, subtract, okay, the work done that we found in part A, and we find out that the internal energy changes, okay, by an amount 5.22 times 10 to the 6 joules. In other words, the internal energy of the gas drops as work is being done on the environment. Okay, so we see here that yes, some heat is absorbed, which you would think would increase the internal energy of the gas, but more work is being done in the process. Okay, so overall there is a net decrease in the system's internal energy. Alright, so the last of the four thermodynamic processes we'll talk about is what we call an isovolumetric process, and as the name would suggest, this is a process that takes place at a constant volume. So Roadkill the lab rat tells us here that sometimes an isovolumetric process is referred to as an isometric process, or sometimes as an isochoric process. When it comes to describing our system, as always, we're talking about an ideal gas here, but in this case we have a frozen piston. Okay, in other words, this is the case where the gas is confined to the cylinder, but the piston is not allowed to move, so the volume will remain constant. What does this process look like on a PV diagram? Well, saying the volume is constant or always has one value gives us basically a vertical line on our PV diagram. This is what we call an isomet. And as we say that the area under a PV diagram is equal to the work that's done by the system on the environment, as you can clearly see here, the area under the graph is 0, in which case no work gets done during an isovolumetric process. So thinking about the piston and the cylinder, obviously if that piston can't move, there's no way the gas can actually do work on the piston. Even though those gas particles can exert a force on the piston, they do not make it move a distance. There is no displacement of the piston, in which case the work is 0. So as you might expect, we are next going to apply the first law to the isometric process. And for the case of the ideal gas, we remember that the internal energy change has this nice simple relationship to temperature. Okay, when it comes to work, we said that since the volume is constant and dV is 0, in other words, the volume can't change, then no work is done, okay, by the system on the environment in the isovolumetric process. So when we look at the first law of thermodynamics, okay, it tells us basically that the change in internal energy of our system is simply related to the heat that is either added or removed. So in the case of adding heat to our system, adding heat to our gas, that causes the pressure and the temperature of our system to increase. And likewise, in the case of removing heat from our system, that causes the pressure and the temperature of the gas to decrease. So looking at a couple of examples here. Okay, the first example we'll look at is the bomb calorimeter. Okay, and here, when we allow a chemical reaction to take place where the volume of this calorimeter and its contents cannot change, okay, we see that, well, certainly the pressure and the temperature can change, okay, yet the volume will remain constant. A slightly more quantitative problem we'll look at here. Okay, what would happen if you were to take an aerosol can containing 2 moles of an ideal gas and throw it into a campfire? Okay, if 5 kilojoules of heat is added to the can, what does that imply about the change in temperature of the contents of the can, assuming it doesn't explode? Okay, so here, assuming that the can doesn't explode, we can assume that the volume doesn't change, in which case the change in internal energy of the contents is exactly equal to the amount of heat that we add. So since we're told the amount of heat added, okay, in the problem, we can calculate the temperature change here. We've got 2 moles of an ideal gas, okay, with 5,000 joules of heat added. Okay, we can solve this for the change in temperature and find out that the temperature must increase by an amount of 200 Kelvin, okay, for this isovolumetric process.